Computer. Okay, I've got the recording controls on there, so that must have started. Let's see. Why don't we go ahead and, if everybody can just mute yourselves for the beginning, we'll get unmuted later for interactive purposes.
What the hell is it?
Okay, so I want to introduce myself. My name is Brian Lane. I'm at Jacksonville University. I'm going to be emceeing this evening. We are here to talk about why integrate computation. Glad to see everybody here. We're going to try to stick to an hour and get wrapped up around 10 p.m. Eastern Time, 10, 9, 8, 7 p.m. West Coast time. So thank you to our East Coast folks for sticking out this late. I've got my caffeine here. So our topic tonight is why integrate computation. So the abstract for tonight is, it's been almost a decade since the American Association of Physics Teachers formally recommended that every physics and astronomy department provide its majors and potential majors with appropriate instruction in computational physics. In this webinar, we'll explore why young physicists need computational skills and why faculty need to integrate computation deeper into their undergraduate coursework. Please join the Partnership for Integration of Computation in Undergraduate Physics for a panel discussion focused on the question, why integrate computation? So what we'll do tonight, in just a minute, I'll introduce our two panelists. I'll ask each of them to speak for a couple minutes just on their experience with integrating computation. I don't think they'll be doing any formal slides or anything. This will just be a nice little panel discussion. And then we'll open the floor for questions, including a few that were previously submitted online. So if our conversation runs slow, I will go to that well. If you'd like to ask a question after our panelists have spoken, you can unmute yourselves, but please be sure to mute yourself back after that. You can also post a question to the text chat, which I'll be monitoring throughout the evening. So feel free to click on the little chat icon and type something there. All right, so I think we're ready to introduce our panelists. So we're going to hear from Rochelle Teeling-Smith from University of Mount Union and from Aaron Titus at High Point University. These are two leaders in the work to integrate computation into physics education. If they could take turns to just introduce themselves a little bit, and please tell us about your experience integrating computation in your individual courses, into curriculum, and in helping others integrate computation. So which of you would like to go first?
I'll go ahead and just go first. So hi, thank you for the introduction. So I'm at the University of Mount Union, which is in Alliance, Ohio. And I find it kind of funny a little bit when you say a leader in terms of integrating computation, because I feel very much just like a practitioner because I'm also a PICUP user myself. So I've worked for many years now on a project called the STEM Coding Project, which is with my colleague, Chris Orban, who is at Ohio State University. And that focus is very much on integrating computation into introductory level physics courses, either introductory college physics courses or high school physics. And so we have a large series of programming modules that have been designed. They covered pretty much the entire introductory curriculum, the mechanics side and E&M, and now we have extras in astronomy and all kinds of miscellaneous topics. But the idea is to take those students in those courses who are very typically complete beginners and don't have any programming experience, and to provide them sort of a video game-like environment. So they kind of program their own video games, sort of their own versions of Angry Birds, their own versions of Asteroids, and all those classic games. And they really focus on the physics because it's designed very much for a physics classroom. So we have some activities that are on PICUP actually that are listed under high school if you select that as a filter. Besides that, though, just as an instructor, you know, I don't have a computational background myself. That's not been my training. So I was kind of a classically trained physicist. So I, as a professor in the classroom, I've had to be, I'm also the student. I'm very frequently in my upper level courses, especially searching for different ways to integrate computation into my own courses. And this is a push that we have in my department, just like people are probably seen in their departments all the way across the country. And so I use the PICUP exercises for my quantum mechanics course, and I've pulled them for electromagnetic theory, for math methods, and so I'm also definitely an active user of the PICUP resources myself. And I'm always I don't have any formal training in Python or any of these other programming languages, so I'm often just kind of jumping in the deep end and learning how to use it myself, sometimes right along with my students, sometimes 2 or 3 weeks before my students. So that's been my experience. So I'll go ahead and let Aaron talk for a minute.
Hi, everyone. I started to use computation in my introductory physics, calculus-based physics in fall of 2003. Actually, I was using the Matter and Interactions textbook by Ruth Shabai and Bruce Sherwood. And I started using that in fall of 2003. And I can honestly say it changed my career. I began using computation for the first time in teaching physics. It very much changed my perspective and outlook and philosophy on the introductory physics course. And so one of the outcomes of teaching computation in the introductory physics course is that my students really got turned on to doing physics in the intro course. And I had a group in 2009, 2010, and they said, if it was possible to major in physics, we would do it. And so we started a degree program in physics that began in fall of 2010. So we grew from 1 physicist on our faculty to 6. And computation was an important part of everything we did from the introductory course. So now every physics course in our entire curriculum has computation woven throughout the course. I saw a quote by one of my favorite Pythonistas. Sorry, Brian, and sorry, Jay. Well, one of my favorite Pythonistas, her name is Lorena Barba at George Washington University. And she said we often talk about teaching students to learn how to code, and we need to talk about coding to learn. And I think that's what's happened is we've integrated coding into all of our courses because it's a tool that students do to learn the physics and to apply the physics and do physics. So it's I've also enjoyed teaching computation to non-science majors and non-physics majors. Back in spring of 2013, I think it was, I may have been earlier than that I started teaching a course called Physics for Video Games, where they used VPython to learn physics and create their own games. And then in more recently, over the last couple of years, I've been teaching honors students a computational modeling class, which is more general than just physics. And I'm kind of excited to maybe share the work of Angela Shiflett. She has an incredible book on an introduction to computational science that I highly recommend. And I've only been able to teach computational physics one time, but there's this great book by Jay Wong. If anyone is interested in a computational physics book, I recommend Jay's book. So that's kind of my overview of teaching computational physics, but more teaching physics with computation.
Aaron, there's a request in chat. Could you repeat the couple of names you dropped there? Yeah. Specifically, the person from Georgetown.
So Lorena Barba, and I'll put it in the chat as well.
Okay. George
Washington University. And I have followed her work and read her blogs for many years. She's a big developer and leader in Jupyter, the Jupyter community. and she's done a lot of writing on computational thinking, what that is. And I'm excited because in 2 weeks, hopefully it will not be canceled due to virus concerns. However, I will be at George Washington and we'll get a chance to interact with Lorena and her team for about 3 days. So I'm super excited about that. Like I don't know, a kid going to a Taylor Swift concert or something. Hope to learn a lot and be a sponge and just hopefully see what other people are doing outside the physics community regarding best practices. And if maybe while we're talking that there was something interesting that I saw them post on, they probably post about 15 or 20 different pedagogical techniques used in teaching coding. And I thought that was a very interesting list, and I recognized a number of those techniques. The other person I mentioned was Angela Shiflett, and her book is Introduction to Computational Science. And she is just a pioneering woman in computer science and in computational science education. And her book is phenomenal. In fact, she has a module on modeling the spread of SARS. So I certainly hope to bring that into my class soon because it's quite relevant.
Awesome, thank you. Well, how about we start off the discussion with our panelists by just asking the question from the title of the webinar, why integrate computation? So what would you two say is the biggest benefit that you see students getting from having computation in their physics courses?
Well, do you want to go in order? Rochelle, you want to keep going first? We'll just make it organized or what?
Sure. Yeah. Okay. So some of the biggest benefits it's been very interesting because I feel like some of the biggest benefits that I've seen have actually been with my students who are not physics students, and even those who are not necessarily STEM majors. So in some of my introductory courses, and I've only been doing this is only my 3rd year, so I'm still very new in doing this, but I'm noticing I've had students actually reach out to me and email me after graduation or later down the line and say very much that they thought it was very stupid when I asked them to do, why am I having to do any sort of programming in physics, because it has nothing to do with what they think the class is about. They don't really see the point when they're doing it. But later down the line, when they either get deeper into their own major, regardless of whether that is in the sciences or whether it's in business or in exercise science or wherever they end up, or later even when they get into their career, they are finding aspects that are actually really critical for them. I had an exercise science major who now does some sort of personal training, I guess is what he does, but he runs his own website. And he goes, the stuff that you taught me, that you made me do, that later when I filled out that evaluation at the end of the semester and I said, I don't need this is not useful for me, this is not useful for my career. Well, it turns out that I actually need to know how to run my own website. And it's actually really, like, I'm really glad you showed me that. And that's one of those emails that, like, you print that one and you save it. That's a very important email. So I've seen students who are not necessarily the students what you would expect, who think who even in real time are going to tell you, this is kind of stupid, this doesn't apply to me, I'm only doing this because you're making me, or I have to. And I've had students come back and say, wow, it turns out that I kind of need to at least understand some of the basics of how this stuff works, just moving through my everyday life or into my career, even not a STEM focused career. So that's been one major benefit that I've seen. And for my majors, for the students who spend a lot more time with me throughout a series of different courses, that's been something that they you know, I haven't had enough years under my belt to really be able to follow them personally to see where they end up in their careers, but they voice appreciation, and they feel that that's a very valuable skill set. So they're the ones who tell me, well, I want to know how to use Mathematica and Python and JavaScript, and they want to know how to use all these different languages, to be sort of language agnostic in that sense, and to have an understanding of how to create their own simulations. So they're voicing this interest, and because they're seeing that as a very valuable thing that they're going to need in the future, regardless of what they're doing. So those have been two of the big benefits I've seen.
My favorite quote in education is that education is not the filling of a pail, but the lighting of a fire. Teaching computation in the intro course gives students a chance to have their fire lit as much as anything else that I have ever tried. And I've had a number of students who simply found something that that they wouldn't have found. It they were able to investigate things and pursue interesting questions that they absolutely could not have done had I not introduced computation in the intro course. So teaching computation will light a fire in your students and in your class. The second reason is there's, I think, one of the most important AJP papers on computational physics of all time was the paper by Alan Cromer. I think it was 1981, where he describes a high school student using an Apple II computer doing an orbit simulation and saying, gee, if I update the velocity before I update the position, I get a stable orbit. If I do it the other way around, it's not stable. And he wrote a paper on that. And the fact that, one, a high school student figures this out is really cool. Secondly, the fact that he wrote a paper, a very, very important paper. And at the end of it, he says, and this is 1981, he says, maybe a three-body orbit will become as common as the inclined plane. Well, it's 2020. We're nearing a 40th anniversary of that paper. You know, it's time for the three-body orbit to be as common as the inclined plane. You can do interesting physics at the intro level if you just teach computation. And my goodness, our students need to learn computation because most of our physics majors will not get PhDs in physics. And of those who do, many of them will need computation. But of those who don't, many of them need computation. So it's just too important to be absent from our curriculum.
Okay, well, thank you both. I guess at this point, we'll open the floor to questions from the other participants. So the topic is why integrate computation. If that's something you are debating or considering, now is a great time to get some perspective on that. If that's something you are interested in doing and you're facing maybe some administrative hurdles or some political hurdles with doing that, you can also ask about how we can help motivate our colleagues to do that. So would be glad to hear from anybody else that's got questions.
By the way, I'll add that I just put the link to Lorena Barba and co-author's book on teaching and learning with Jupyter. But chapter 4 is a list of probably 23 or so, 22 technological, or sorry, not technological, but pedagogical practices.
So how do we ask questions?
You just did.
Oh, okay. In that case, I'd like to ask a question. My name is Sam Cho. I'm at Wake Forest University. And one of the reasons why I joined in here was because, so I've been using matter and interactions for 2 years. And so I've been using that in my intro Physics 1 and Physics 2 classrooms. And the other reason why I joined in on this conversation is because our department is considering introducing a computational physics major. And so we're at the early part of that discussion. And so when Aaron mentioned that he has an entire curriculum that has computations integrated, I was pretty excited to hear that. And also, hi, Aaron, how are you? So my question that I wanted to ask was, if you were to have computations involved in many levels, do you have a consistent environment? Because one of the challenges, at least for our department, is that somebody knows how to do MATLAB, somebody knows how to do Python, and then there's me who knows a lot of different things, but I don't really have the bandwidth to train everybody on everything, right? So what has been your approach? And let me mute myself.
By the way, yeah, hi Sam, good to see you. Sam and I are about 30 miles apart here in Central North Carolina, and I need to see him in person more often for sure. So I mean, we've been using Python and Jupyter now pretty extensively. Once students are beyond the first year, we use glowscript.org and VPython in the first year, and Trinket. However, I don't know if I have a great answer on that, except I think that maybe the best thing going forward is that students develop I would say a willingness to use various tools, or to use whatever tool they need for the job, and to separate the tool from the job maybe. So let's say in a computational physics course, you're teaching them one thing, but then maybe in another course, that professor who's teaching that course uses MATLAB for everything. I think they can teach the technique or what they want students to learn or do computationally, and then I think students could potentially use the tool that they're most comfortable with. And so it may be that the teacher shows them how they would do it in MATLAB, but then a student would actually do it with whatever tool they're accustomed to using. I know that might be too flexible, but it might allow students to really see that you can solve the same problem with different tools, and that could be really valuable.
I would probably echo something that sounds almost exactly like the same answer. So I don't know how helpful that is. But, so I'm coming from a very small department. And, for us, as you use the word bandwidth, and that's the problem that we have. And so we're trying to integrate computation across the entire curriculum from top to bottom, but it's kind of just whatever we're each individually able to piece together in real time as we're trying to put the courses together. And everybody's got a full teaching load, and they teach completely different courses each semester. So I'll teach a course, I'm teaching a course in quantum mechanics right now, and I won't teach it again for 2 years. So any change I have in mind that I want to make, I got to either write some really great notes, or, there's a long time to turn that around. So we kind of have a similar approach where I have one colleague who he does everything in Jupyter notebooks, loves those, and those work great for the class. So he does a couple astronomy courses and a couple intermediate level courses, and the students are seeing the Jupyter notebook approach in those courses. I have another colleague who is teaching the computational physics course for our department, and he just sticks to Python for that course, because that's where his area of expertise is. And I try to just kind of sample from a variety of different systems. So I use everything from VPython to MATLAB to Mathematica to Python. I use Jupyter notebooks, kind of with the idea that just echoing what Aaron said of kind of decoupling the problem from the tool. And I'll have some students, if I have a student who's more sophisticated and is like, well, I really wanted to do this in, I'd really prefer to do this in Python rather than to do it in MATLAB. Okay, excellent. But I'm also dealing with small classes where I only have a handful of students. And even then, sometimes that you question about how manageable that is for me as an instructor to hope that I have enough expertise in each one of those to keep up with what my student is doing. The answer is mostly yes, but not always. And then to be able just to accommodate how I'm grading and how I'm assessing what they're doing when everybody's doing something a little bit different. It gets to be, it can quickly grow to be out of hand, get out of hand if you're working with a bigger group. So that's a model that's worked well with us as a really small department, where and with with everybody in our department being on board with this as an objective. But that's not necessarily, it could be definitely more challenging for somebody who's coming from a different environment where they're working with much larger class sizes, or a much larger department where not everybody wants to participate in this initiative. So I don't know if anybody else besides just the two of us, as anybody's coming from a completely different environment, might have some comments on how it's worked for them. That would be valuable here.
Yeah, any other feedback from any of our other participants for Sam? One thing I'll add is the students that come into my class have already had to learn a few different systems. A lot of them, they've learned Maple in their calculus class. They've learned GeoGebra or Desmos in high school. And so by the time they get to my class and they're doing Python, they're on their third language already. So it's probably a valuable skill for our students to learn, is to navigate through multiple environments. Any other feedback on Sam's question?
I guess I'll add to the previous, comments by saying I'm torn between having different platforms versus I guess sustainability, right? All of you know that by doing this is something new, and to keep it going, you want to make it as easy as possible. So if you want to do this, through the courses, have them stick. Having different platforms is certainly a very challenging thing. So, but there are, like Brian says, right, there are good points to it. Engineers use MATLAB, and a lot of our students use, Mathematica and whatnot. So what we've done here is that at UMass, we decided to require, years back, to require students to take a scientific computing course taught by math folks. They use Python, and that kind of sets a tone. So pretty much everything we do here is, Python, Jupyter Notebook. And so I'm saying there are pluses and minuses, but I think from our experience, it seems like it's easier if everybody could agree on something or to keep the platforms, to the minimum. But, if people want to do Excel, I don't think that should be discouraged, right? It's just tough to let's say, like Rochelle says, right? If you end up not teaching this class, somebody else steps in, that means, computation may just get left behind, so.
Okay, why don't we, sorry, Sam, were you gonna say?
Yeah, I just wanted, the reason why I brought this up was because if you keep on changing platforms, it takes time to train the students to learn how to do something. And I suppose you can point them to videos or online courses or stuff like that. And that isn't that effective. And so I'm also a professor in the computer science department, and we recognized this a long time ago. And so although it is a very valuable skill to be able to switch from one language to another language as a computer scientist, for a computational physicist, I would imagine that you really want to focus on learning physics. And so if you're constantly learning new computational tools all the time, it's really easy to get lost in it and to get stuck in, oh, I'm learning this other new tool. And then you start losing sort of the magic of the thing that we're trying to teach, which is physics. So, but I understand, there's definitely the real world aspect of, we all don't have time to like learn all these or try to. It's really difficult to get everybody on the same on the same page. Yeah, just that's my 2 cents.
Okay. Well, thank you, Sam. And if you don't mind, I might pick your brain after this session ends, follow up on your process of creating a computational physics major, because that sounds exciting. Why don't we go to a question that was submitted online. So for our panelists, how do you find time to fit computational techniques into an already jam-packed lower division physics course? What do you drop?
Well, I can tell you a little bit about what we did just in our just our 100 level courses. And so basically we squeezed them into the labs. That was the most natural place to fit them. So our labs were already very modular in nature. So each time the students come in for a 100 level lab, they're doing 4 different short activities, and they rotate through, and so they're completing 4 of these short experiments. So that was the simplest place where we were able to basically substitute out throughout the curriculum, probably only maybe about 10%, less than 10% even, of the hands-on activities, and replace those with sort of having them program simulations, or having them, kind of, we use the video game approach because that's where I've been working. But that's been a nice, easy way where we're still doing our best to hit the same learning objectives. We're hitting the same topics. We've designed assessment questions, which would be very similar or the same as the ones we would be asking them to answer in the lab anyway. And just having them do that as a computational project instead of as a hands-on project where one person, fires the projectile and they measure where it lands. Now they're, and then they would use the, set the equations to, validate all the different parameters that they would find from that problem. But now we have them do that as a computational project instead. So it's a little bit, you are losing a little bit in doing that, because you're losing some of those hands-on experiences. And we're trying to measure what the impact of that is on the student learning for those topics is a really interesting problem that we're looking at right now. But that's been where we have found the time to do that.
Yeah, definitely. I think lab, it all depends on how your course is structured, right? You might be doing a studio class that has no separation of lecture and lab and so forth. So, to me, the question isn't kind of where you put it in, but how many hours are you going to devote to it? And, for us, it is during our lab time mostly. And we devote roughly 40% of our labs to computational activities. And then some of the class time, lecture time, can be devoted to computation as well. But I think it's really important that it is done with students together in person. I think giving students a computational exercise outside of class when they've never coded before, and they might even doubt why they are being asked to code in a physics class, it's really important to do it with them and not just relegated to outside of class. So I think for me, a big, very important aspect is changing your curriculum. I go back to what Alan Cromer said almost 40 years ago. It's the 3-body problem should replace the inclined plane. And so the question is, if you're going to teach computation, how does that impact what you're teaching? and are you evaluating what you're teaching? And I think that there are some things we're teaching that we just may not need to teach. And when you're doing computation, you can actually also teach an iterative approach to thinking about dynamics, for example. But think about a problem that I really, really like and have always done is computing the electric field around a uniformly charged rod or a uniformly charged ring or disk. You can only do it along a symmetric axis analytically, but when you show students how to do it numerically and that you can find the field at every point in space, that's a game changer for what you're teaching regarding fields in the E&M course. And also I recommend combining computational modeling with lab. So I didn't just replace the lab, it's enhancing the lab because, and by the way, have you noticed physics labs take a lot less time when you're using sensors? When you're collecting the data with sensors and you're using computers for the data analysis, you may not need 2 or 3 hours to do the same old experiment that you would have done 40 years ago. Some of those experiments just don't take as much time since you're using sensors to collect the data. So therefore, you have time to do a computational model of the thing that you just did an experiment with. So you can combine the modeling and the labs so that you don't really lose anything. You can be more efficient.
And I think where you do that, you're actually helping the students see the computation as a tool to help you understand the physics as opposed to another type of assignment that you're giving them.
That's right.
Yeah.
And my favorite example of this is for years I had students compute the electric field around a charged rod numerically and display the field at various points in space. Well, a year ago I decided, there's a great video of an astronaut on the space station, and he takes a charged rod and he releases a charged water droplet, and the water droplet orbits the charged rod and it gets out here and then it comes back like this. And so we just made estimations and then did a computer model of that. It turns out what we found is that is a hard activity for students to do because it was the first time they needed a nested loop. So they have a loop in time, but to model the motion of the water droplet, then for each time step, they have an inner loop that computes the electric field by iterating in, over the rod to find the electric field. And that was a cognitively difficult task at the intro level. But then I had some students who finished it and were exploring tremendously interesting orbits for the water droplet. And so that's a good example where there's something real and tangible there. This is a real video of a water droplet orbiting a charged rod, yet it was something that they had to model because they didn't have all the parameters to analyze the video itself.
Awesome. Other questions for our panelists? You can either unmute yourself and ask it audibly, or if you want to submit a question to the group chat, you can do that as well.
Yeah, just follow up on Rochelle and Aaron. So you are there doing the computational activities with the students, or do you also have like TAs either helping out or run, standalone sessions in the lab component?
So all of our labs are pretty small in size, and we have a lab instructor who is there with the students each time, and they have a TA in the room as well. And so that's definitely a consideration, is that there was an investment of time in training the lab instructors to run through all of these different programming activities and programming modules. And then to do the same thing with the TAs. Now, what's been good is that, with the lab instructors, we at least have the consistency from one semester to the next, and it's almost always the same person who's teaching the labs. With the TAs, that's an entirely different story. So at the beginning of each semester, there's definitely an investment of time where I'll sit down with the TAs and log them into the system and show them, you know, kind of how the modules are run. And so yeah, that's definitely a consideration. It's definitely not zero cost.
I have a TA that is just there during the lab to help me answer questions for my larger lab sections. You know, if you have 20 students writing programs that are a little bit open-ended, they're given a task and maybe shown how to do something, but it's not just telling them type this and type this. They're going to have a lot of questions, and it can be hard to run around and answer those questions. So, you know, I find that if I have 20 or more in a lab section, I do like having a second person there to run around with me, just to help students troubleshoot. But I know Ruth Shabai uses the same computational activities that I do, and she has TAs who teach the lab without her in the room. So these are something that a grad student is implementing.
Okay, let's go to another pre-submitted question. Do either of you know, has anyone looked at the effectiveness of spreadsheet-based computational labs and activities for high school level computational integration?
And I really don't think a lot of work has been done on teaching effectiveness actually in teaching computation in the context of physics or even STEM disciplines. I think it's a pretty open area for educational research. Maybe Brandon can pipe in on this. So as far as effectiveness goes, I don't think, I've not seen anything on effectiveness of teaching computation with spreadsheets. I just think not a lot of research has been done.
Oh, Brandon asked to repeat the question. Basically, has there been any research done on the effectiveness of using spreadsheets as your programming language, particularly at the high school level, to make activities based on spreadsheets? So Rochelle or Brandon, either one of you wants to chime in.
I
Can
mean,
everyone hear me? I do not know if there has been any research on the use of spreadsheets, either at the college level or in the high school level, which I guess answers that question. I have been using them in my sophomore level Python lab course. I think they're, I've actually learned a lot from Kelly showing us them during PICUP workshops, but I think they're a really good way to help introduce some of the ideas of iteration with, and some of the ideas of computational modeling, because it shows the iteration right in front of you before it starts getting hidden by while loops and for loops and things like that. No, I haven't seen any research on that.
And I would only echo the same thing. I've definitely used these as a project in courses here and there, because you're right, it does kind of demonstrate that how students can use iteration as a tool for kind of developing like these little simulations. But yeah, I agree. I haven't seen anything in regards to any sort of research on effectiveness of this technique. So not that I'm aware of.
By the way, I'd like to add one other thing, and I'm going to try to search for this so I can send you the link in the chat. We had a colloquium just this last Friday by Ann Leek, who was a postdoc at RIT that worked on the photonics sort of industry and physics education connection. And she's working with I think Crystal Bailey at AIP on the entrepreneurship project. Are people familiar with this? It's an initiative by not AIP but APS. It's an APS initiative to bring entrepreneurship into undergraduate physics programs. And there was a Physics Today article certainly within the last 6 months. If anyone can find it, I'm going to look for it as well. But I think Crystal Bailey's the author. And that may have some data in there, but in this colloquium, Ann Leek told us basically students need to know spreadsheets when they go to work in industry. So there's the physics education research, how effective is teaching computation with spreadsheets? And then there's just the practical side. What do our graduates need to know when half of them roughly are working in going to industry after they graduate? And one of the things they need to know is spreadsheets. And I can honestly say my students are not getting enough experience with spreadsheets.
Yeah, I think
I was just gonna, Brian, just gonna echo since the spreadsheets come up. I don't have any research, but I've got about 15 years of anecdotal observations, at least on a college level. I don't know about high school, but my conclusion is they're damned effective. How's that sound for a research conclusion? I don't know if it's gotten into the high schools yet. In my humble opinion, it should. But to echo Aaron's sentiment, I rub shoulders with a lot of engineers. I don't know if most of you know this. I live with engineers now, not just my wife, but I actually am in an engineering department. And this is one of the things that engineers reach for on almost a daily basis. And so we have got to get our physics majors using spreadsheets. However, one other, before I mute and be quiet the rest of the night, I don't just use it as a tool for calculating things. I use it as an on-ramp to get my students into the programming languages as fast as I can. And that's where I have found the most usefulness of spreadsheets. And I think it's been pretty effective.
Yeah, I think in general, the effectiveness of any kind of computational stuff, regardless of platform, is on the PER to-do list. I think I mentioned that at the last summer meeting. So we are coming up on 10 minutes left in our hour-long meeting. Are there any other questions people would like to pose to our panelists before we wrap up? Yes, Adam, I see that hand.
Oh,
Hey, Adam LeMay here from University of Central Florida in Orlando. I'm a longtime listener, first-time caller. So I'm curious as to what sort of platforms y'all are using. Let me tell you a little bit about what we're doing here. At the university level, not a whole lot in our physics department, which is where I work. But I do a lot of collaborations with our K-12 school districts. And we have this rapidly growing project for middle schoolers to use what we've designed as Jupyter notebooks, but hosting them on via Google Colab, and that really seems to be hitting a sweet spot with usability. I've been a fan of Jupyter for a while. I started hosting my own Jupyter Hub server on AWS and got bogged down, and then Binder was great, but that is too fickle for production level, rolling this out to 15,000 middle schoolers. And Google Colab has been fantastic. Is anybody else using that, or is there anything else that should be on my radar?
That's a wonderful question. I think it especially dovetails into the need that I think a lot of us are about to be facing of delivering course material online within the next week or so. So yeah, we'd love to hear from our panelists or any other veterans about platforms that they like the best.
I want to have a big long discussion about Colab with Adam. This semester I had to make a decision: use Google Colab or use have students installed Anaconda with Jupyter, locally. And then I am actually using a product called NB Grade, which maybe you've heard about. And because I'm not using Jupyter Hub, which I've installed on AWS, and it's very hard to do. But because I'm not using that, I'm actually using Google Drive with 23 students, and I wrote my own scripts that take their programs from each of the shared Google Drive folders and grabs them all and puts them in a spot on my computer where I can then run them through NB Grade. The downside is that I can honestly say many students cannot download a file from Google Drive, edit it locally, and then upload the exact same file to the same place from which they downloaded on Google Drive. I would say roughly only 70% of my students can do that consistently. And some students could do it for 2 weeks and then all of a sudden couldn't do it anymore. And I've got some funny stories to tell why that happened. But I'm curious about Colab because I really wanted to use Colab. It's meant for this, but I ran into not fully understanding how I could set up sort of a file structure within Colab. And it's like I could open a file in Colab, but I couldn't really deliver sort of a set of files and things with Colab. I struggled to use it. And so I'd like to learn more about it too.
I'll reply to that at least. I have used Google Colab exclusively for at least the last 2.5 years for this type of thing, just because it's so much easier. But for some reason, it's really laborious to have your stuff hosted in Google Drive, reading from a file that's also in Google Drive. But it's like one short line in Pandas if you're reading something from a GitHub repository, right? So if you host all of your notebook files and any sort of, CSVs or text files that you're reading, if that's in a GitHub repo, then you can create this link that it starts off googlecolab.com/ with your repo information, and then when somebody opens that link, it'll open up a Google Colab window, but read it from your GitHub, and it's crazy scalable as well, right? Because it's drawing on Google's resources, not mine. Yeah, I'll give a shameless plug if you want to check out codingink12.org. I'll put it in the chat window here. That's my best stab at coming up with a catchy URL. But some of our K-12 stuff is on there, and I think I have a little blurb on how to set up your GitHub and Colab to get them to talk. Yeah, the upside with that has been right, that students don't have to do their own install and transfer files. The downside is that they're relying on, it's a 95% Jupyter-esque interface, but it's not a local install. And I think for university students who are going to use this more than a couple times, I'd probably want to go for Anaconda. I don't know. Anybody else?
I'd just like to throw out there, I think Adam should give a PICUP 2-hour tutorial or something on how to do that, because as an experienced Jupyter person, I literally couldn't set up Colab to use it for my class. And you know how to do that. I went to one of your presentations at an AAPT meeting, by the way, and that's the first time I learned about Colab and was very impressed. But I think doing some kind of workshop would be great. Maybe an AAPT workshop, maybe a PICUP workshop.
Heck
Yes.
yeah.
Adam needs to be careful. He'll be a first-time presenter soon. We get one more question in the. Oh, sorry. Please go ahead.
This is Trina, and my camera obviously is not working, so I'm just a voice in the dark. But this is my first time to be at one of your sessions, and I did it because I've heard all about computational physics, and the name is leading me down an interesting path. And so finally I decided, all right, I need to pay attention to this. And what this reminds me of is when everything else was first introduced into physics, like handheld calculators. All right, everybody's got it. And I'm telling you, I know some teachers who were excellent refused to pick up the handheld calculator. Still use their slide rule. And also it reminds me of trying to get the sensors from different industry in. So everything's changing the way we collect data. So what I perceived this to be, and that was one of the reasons I was never clearly sure what this was all about. It sounds like instead of just taking a verification lab and saying, yeah, we figured out what Planck's constant is or whatever, that you're looking at a variety of ways to use this information as conditions change. And so it's taken the whole idea of a physics lab out of a one item situation into an expanded way. Now, I could have that wrong, and feel free to correct me, but I'm absolutely fascinated. But what it's telling me is that I am going to have to become proficient in a language so that I could introduce this through my labs. I'm in a 2-year college, community college, and so we have students who come out with their associate's degree in STEM, whatever that means. And but to have pure physics majors, we have to send them on to the 4-year schools. But we do have some students that are very gifted that do show up in our classes. And I'm just thinking that this would be an excellent addition. When I was teaching in high school, I did have a spreadsheet lab that I let my students do. And I did have some high school students come back to me later and say, I'm so glad we did that because, and I thought, okay, there is success somewhere. But anyway, I appreciate all of you sharing and allowing me to be part of your group tonight, although I'm sure nobody asked what I was there for. But I think I might have to tune in again to hear more about how you're allowing these changes to occur. And I've heard some of you give papers, so okay, I was almost there. But anyway, I do appreciate you letting me do this.
Well, thank you, Trina. I don't know if you're familiar with Joe Hefner. You can follow him on Twitter. He's also in a 2-year college environment and does a lot of the computational matter and interaction stuff. Speaking of getting plugged in and hearing about sessions and everything, we are coming up on time, so I did want to wrap up with a few reminders. PICUP has its first ever capstone conference coming up this summer. Registration is open. I don't know whether it's filled yet. I'm guessing not, or else I'm sure Brandon or Kelly would be correcting me on that. So I think the goal is to get folks who have been to some sort of PICUP workshop before, so and just hear about what people have done with what they've learned. Also, I'll give a reminder that PICUP maintains a very active Slack channel. If you are not in that, I don't know if I can push a link out or if you have to request, so you can reach out to me and get that info. Also, you can go to the PICUP website at gopicup.org, and that'll have contact info there as well. We'd also be glad to receive any suggestions for future meeting topics. If you'd like to reach out to me after the meeting, I'm on Twitter at Let's Code Physics. And I'll also be posting all of the links that Aaron and others have shared in the chat to the Slack channel after we break in just a minute. So yeah, I do want to thank our panelists, Rochelle and Aaron. Thank you so much for joining us. Does either of you have any parting words of wisdom for our folks who are gathered here tonight?
I just look forward to learning from others. I've learned much from Sam and from Jay, and I got to learn, and of course, you all too, Brian, and I look forward to learning more about Google Colab. So thank you for giving me more work to do tonight.
I should mention Aaron agreed to be here because I corrected a typo in one of his codes, so he paid me back by agreeing to do this panel.
And the only thing I would say was just thanks for having me. And this is always kind of a fun place to learn new things. I'm over here copying links really fast before they disappear myself because there's always new things to learn. So thank you, everybody.
All right, well, that'll wrap it up for tonight. I want to thank everybody for joining us. And like I said, if you need to get the Slack, let me put my Twitter handle in the chat. You can reach out to me there and I can get you invited to the Slack channel if you need that resource. So thank you all. Hope you have a wonderful evening.
So Kelly, so the workshop is off. Unmute it, please.